Hello, good morning. Wait. So, hold on. Uh, testing, sound testing. Is this working? This is working. Yes. And what else? I have my screen here. And wait, I need to change something because wait. Oh, because all right. And now you can hear me, I think, correct? Yes, you can hear me here. And then now you should be able to hear me here. And if I now go back to desk, now you can hear me even though you can't see me. Hello. That's it. There you go. And wait, I still need to the green screen. All right. So, okay, here we go back. All right. Good morning, everyone. How is everyone doing? Welcome. Good morning, good afternoon, good evening, whatever you are. Let me adjust this. There you go. There you go. Good morning, good afternoon, good evening, whatever you are. This is Jose Luis here. This is Parametric Camp. This is for those of you who are new, we do live streams. We go live mostly every week, hopefully, not always. But I have a very busy fall semester, as many of you already know, so I struggle to find time to make this happen, but roughly once a week. And we go live, we record tutorials, we edit them, we post them online, we do playlists. It's fun, it's great. I get to hang out with like-minded people, so it's pretty awesome. Now, I was testing a couple things here and there because, as you may have noticed, today I am not wearing my typical microphone that I typically use for recording because it was my birthday yesterday. And if you know Nono Martinez Alonso, alias Nono Ma, he just sent me this thing here as a birthday gift that I am testing today. See how it works. You may notice that the sound is slightly different, but I've been testing things out and I hope that the level of the sound and the noise canceling is working good. So we're going to give it a try. And it's going to be, I'm very excited about this because like this thing, the sound wasn't great. Like it uses a lot of batteries. It's like not environmentally friendly. And this is a much more resilient solution, I believe. So it's going to be great. I just bought an arm so that I can, instead of having it here, I can like hang it from. It's gonna be awesome. All right. And I also discovered that in OBS you can do GPU based noise canceling, which is awesome. So I'm noise canceling the background noise with my graphics card, which is kind of very cool. All right. So what are we doing today? So, if you remember, we were in the middle of recording this playlist called Advanced Development in Grasshopper. So, so we are going to continue doing that, and today is going to be extra cool because we're going to do this thing where what are we doing today? We're going to so last time we did recordings I showed you how to use the C# script component to perform calculations that felt like continuous execution. So how to create variables that were persistent and that kept their values across different instances and different executions of a particular component. So I'm going to use that today to do an example of to do several examples of dynamic simulations. So if you have ever used Kangaroo, we're going to write a lot of Kangaroo-like components today. All right. So that's going to be actually quite cool. Kartik, good morning. How are you doing, fellows? Okie dokie. So shall we get started? We're going to get started. So I actually have an example of what I want to achieve. Yep. I actually have an example of what I want to achieve here. So I'm going to be looking at this code every here and then. I may just like copy paste it like right over here, just to make things a little easy. All right. Okay. So how are we going to start this? We are going to start from the beginning. That's typically a good place to do. And what's the beginning? Well, the beginning is typically the introduction video, with the introduction clip, which I probably want to do later on. And but we're going to start with a. Okay, we're going to start with a. Am I going to need to draw stuff for this one? Am I going to need to draw stuff? Should I set up my drawing board? I don't know about that. I need to think about that. I may need to draw some sketches. Okay. Let me think through this for a second. Let me think through this for a second. Well, maybe, but we'll do that. We'll do that whenever I need to. Well, we'll just assemble that thing whenever I need to. I need to actually do it. So, all right. So, how are we going to start? Should I start already with some? Let me just punch here some. Okay. With I'm going to right, and then just start with the point. The do R and let's just do L for no particular reason. Okay. Anyway, I'm going to introduce. Yeah, I think I'm gonna need to. I think I'm going to need to draw on a screen. All right. So give me a second because I'm going to set up the whole drawing board, etc. And it's gonna take me a couple minutes. So hold on, stay there. Don't go anywhere. Go anywhere. Blah blah blah. So we're gonna need this. We're gonna need to plug this number. Okay, so that's there. And I'm going to need to replug the microphone probably, but the microphone is very much in the way. Let's see if I move it here. Maybe this works. How's everyone doing in the meantime? This is not. I should prepare things in advance, correct? This is not. I do this, right? And this goes here. Yeah, I'm going to need to draw on the sketchboard. And so now, so I should be able to project to my wireless device. Exactly. Oopsies. There you go. And then I should be able to run a sketchbook on my other. There you go. And now I can do, hi, how are you doing? Whoa, ho, ho, look at this guy. Whoa, whoa. All right, so that works. And I'm going to dock this here. I'm going to dock this there. I'm going to do a new file because this sucks. Okay. And so I can go back here. All right. Well, if that's the case, then the first thing I want to do, you can hear me, right? Can you hear me? Because YouTube's still telling me that there's no sound for some reason. Can you hear me? Okay. Yes. All right. Hey, Victor. I didn't know you were there. Good morning, or good evening in your case. No? What is your time? It's probably like very late, right? Close to 10 p.m. Um, all right. Now, okay, so then I'm going to switch here and then I'm going to draw. Basically, I'm just going to draw a rectangle right here. And so that's going to be one layer. And then I'm going to draw like a tiny point here, one layer. And then I will, I will do like, okay. All right. Um, Okie dokie. So the video would be the introduction, and then we would jump to drawing the sketch. So we would jump to this, and then I would explain what we're doing, and then I would explain what we're doing and how we're going to move. We're going to use a particular direction. Yes. Direction, and then we will, after that, working. Oh wait, it is working, but not for me. Weird. Wait, wait, wait. This is very strange. You can see the drawing. Something is failing very catastrophically. Good morning, Andres. This is very strange. Something my okay, my sketchbook just failed really badly for some reason. And if I open it again, I can draw. But where are the layers? Windows, layer editor. Okay. Well, that failed pretty bad. Okay, so we're here, and then we start with a location. We start with a vector, and then okay. All right. So let's do this before things collapse again. Okay. All right, so let's start with the fun. So the first example that we're going to do is going to be super simple. We're going to imagine we have some kind of region that is defined by a boundary. And to make things easy, we're just going to choose a rectangle. And then we're going to start with a determined location. So we're going to start with a starting point, and we're also going to define some kind of starting vector, which is going to define the initial direction of motion. And what we're trying to do with this exercise is that we're trying to create a simulation. We're going to try to create a simulation that is going to make this point move in the direction of the vector with the speed of the vector. So every step, we're going to move an amount that is going to equal the length of that vector in that direction. And then as the simulation evolves, as we hit the regions, we're going to start bouncing back, and we're going to create something of the kind that is going to just be moving around and bouncing off the region boundaries, etc., and create this evolving pattern of I don't know. I don't know what that is, but it's going to create this kind of simulation. Okay. It's going to be super easy. You're going to see. So let's take a look at how to do that in Grasshopper. Okay. And then I'm going to go back here. The start point is going to be start velocity. So I have gone ahead and created a C# script component that it has a few inputs already. So it has a starting point, a starting velocity. So this is going to be a vector, that vector that defines direction and defines magnitude as how fast this point is going to move every iteration. And I've also defined width and height as a simple way of defining the boundaries of the region, right? And we're going to start very simple. So I'm going to make sure that I don't forget to specify the types of the inputs. So the starting point is going to be a point 3D. The start velocity is going to be a vector 3D, and width and height are just going to be numbers with decimal part. So you can't see it on my screen. It's flowing on my other screen, but that's going to be a double, and this is going to be also a double. All right. And we're going to start super easy. What we're going to do is, first of all, just for the sake of visual, we don't really need this, but just for visual reference, I'm going to create a rectangle that is going to live within those two boundaries. So I'm going to define a rectangle in Rhino Common that I'm going to call, for example, the boundary. And this is going to be a new rectangle 3D. Actually, rectangles are rectangle 3D. That's the name of the class. And then as I open, you can see that it asks me for a base plane. We're going to simplify this example, so we're not really going to account for the possibility of simulating this in 3 dimensions. And in order to do it well, we should actually take the point and project it into that plane, etc. We're going to oversimplify it a little bit, but you, the viewer, you're welcome to extend this example and make it better and more resilient and more all-road in the future if you wish so. So I'm going to keep it easy, and it's going to just choose the world XY plane for this rectangle. And then you can see that I have a constructor that gives me the width and the height. So I'm going to plug those right away, okay? And for the sake of visual representation, I had two outputs on the component right now, R and P. So I'm going to use R for the rectangle. So that's going to be boundary, okay? And as we've been doing in the previous example, so this is going to be all the algorithms that I'm going to write, and then the output is the boundary. If I do that, and nothing happens because I don't really have values associated here. So let me plug in a few numbers here. So this is going to be the width, and now this is going to be the height. And you can see that I got this rectangle that is really large in space. And if I plug in a panel, you can see that I have a rectangle, which is actually more like a square at this point, but whatever. So beautiful. Let me take a second to create a couple of points and vectors that I'm going to plug in here in the input. Let me move this right over here, and then the starting point is going to be this, and I'm going to set one point over here. Okay. Then I'm going to create another point, set one here. Okay. And then vector between 2 points, A and V, and that's going to be the starting velocity, and that's going to be display vector display between this and this. All right. Okay. I'm going to save this as something because otherwise dynamic simulation. Okay. So what I have done is I have gone ahead and in Rhino, I have created 2 points that I have brought into Grasshopper by referencing them, the one on the left and the one on the right. Okay. And the one on the left is the one that I'm going to be using as a starting point. And the one on the right is going to be just a secondary point that I'm using to define the velocity, which I'm defining as a vector between the first point and the second point. So that I'm also visualizing here. So this point is actually useless, but I'm using it to just easily to have like a drag of like, how to set up the initial speed rather than having 2 sliders, which sometimes is a little not so nice, all right? So but you could choose like a vector that you create with your sliders, etc., as a way of doing this. Beautiful. So now I have a starting point. So I have the rectangle, I have the starting point, and I have a starting velocity for the point to move. At this point, we are in a very similar position to the example that we did in the previous video on this series, where we just took a point and we made it move along a vector. So we're going to try that, okay? So if you remember, in the previous video, I explained that in this area of the C# script component, because we are inside of a class, I can just add more members to that class. What that means is that I can create variables that live outside of the main run script function, and those variables, whichever values I give them, are going to be persistent, are going to survive over different iterations, different executions of the component. So what I can do here is I can say first of all, I'm going to create a point 3D that I'm going to call location. And this is the variable that is going to store the position of the moving point at any point in my simulation, right? Let's call these frames, for example, at any iteration of my simulation. And I'm going to start it with some random values. So for example, I'm going to start it with unset, okay? And then we also discussed how it's typically useful to have like a reset flag so that you can signal to the component that you want to start with a particular, you can start when you press a button or when you signal that flag so that things reset and then we can kick off the simulation. So I'm going to go ahead and add here another input. I'm going to call this reset. I'm going to call this reset and I'm going to right click and make sure that this is of the type Boolean. All right. And I'm also going to plug in here a Boolean button. All right. And then so this on, reset, not reset, etc., etc. So what's great about this is that now what I can do is I can say in my algorithms, I can start by saying if reset equals true, or we know we can short this. If that is true, what I can do is I can make sure that in this particular iteration, I take whatever the point location has as a value and I override it with my starting point. So I'm going to say location needs to be equal now to my starting point, but only when I reset. After that, location should get whatever value that is coming out of the simulation. So at this point, this is working and I don't get any errors. All right, so that's great. So here I am drawing my boundary. Okay, but again, I only need this basically for visual flavor. So I'm going to just push this all the way to the end. And then what I'm going to do here is that if I'm not resetting, okay, what I should do is that I should take the point and then make sure that I move that point with the vector that defines velocity. So we saw that in the previous example. So I'm going to say update location of moving point with velocity. So I'm going to say location, not starting point, because starting point is always going to be the same, but location is the one that needs to change. Location needs to change at a rate defined by starting velocity. Okay. All right. So let's see if that works for the time being. Oh, and I forgot that over P, the output, I want to be outputting the value of location because this is the point that is going to change over time. So I'm going to reset this and you can see that I already, only by pressing the button and releasing it, I've already executed like 2 instances of my simulation. And if I were to put here like a trigger component that resets every 200 milliseconds, you can see how the point is starting to move at a rate defined by this velocity. And if I press the button again, you can see, can you notice the slight difference of like how I press and then it's already 2 steps ahead? I'm going to modify this and I'm going to say, if I'm pressing reset, then make sure that you reset, that you set new values for all these persistent values and you don't execute anything else. So if reset is on, just don't execute any of the remaining code. All right. So that would save me one execution of this. It's just that also because I'm stopping the component, I'm not getting the rectangle, but that's fine. Okay. Beautiful. So this is working. Okay. But now how can I make the point bounce over the boundary of the rectangle? Well, there's a couple ways I can do that. So for example, the idea here is that when I know what I would need to do is I would need to do something whenever I know that the location of my point is beyond the width of the rectangle. So what I would need to do here is I can say if location.x, so that is the location of the x location of my point. If this is greater than either width as a value, or if my situation was a bit more complex, what I could do is I could have created this earlier, all right? And I could say if the location of x is greater than boundary dot width. So that could be another situation. Or if let's just keep it like that. All right. If this is greater than that, then I would need to do something. What is it that I need to do? So for example, right now, I'm just going to print a message out of bounds. All right. I'm going to execute this. I'm going to put here a panel. I'm going to run my simulation. And I'm going to restart it, and then it's going. And you can see it's out of bounds, out of bounds. It's out of bounds. So what I need to do now is I need to make sure that if I am out of bounds, what I need to do is I need to change the direction of the velocity. If the velocity is pointing to the right, then what I need to do is I need to make sure that it points to the left. What that means in geometric terms is taking whatever the value of the x coordinate of the vector is and making it negative, correct? So you might be inclined to say, well, if this is true, then what I need to do is I need to say start velocity dot x is going to be equal to minus start velocity dot x. Okay? So I take the velocity and I flip it. This could be a good intuition, but let's see what's going to happen. This is not really going to do anything because if you think about it, start velocity is a value that is always coming from the outside. So the component is always taking the value of start velocity, which is given by Grasshopper, is whatever this is, right? And by the time this executes, start velocity always has the input value. And if I change this, and if the point goes out of bound, yeah, well, I'm flipping the x coordinate of the input velocity, but I'm not using it anywhere else in the code. I've already used the one that doesn't have the flipped value. And because that's the case, and because start velocity on the next iteration is going to go back to whatever value is coming from the input, this will not work. So what I need to do is I need to make sure that I have some kind of more persistent value of the velocity, which I can use constantly and that I can change. And if I make changes, those changes stay for the next iteration of my simulation. So what does that mean? What that means is that when I start the simulation, I need to create a persistent point that I can change over time. But I also need to create for example, vector 3D current velocity, okay? Which I also can start as unset. And then what I can do is when I reset my simulation, what I say is current velocity needs to be equal to the starting value. All right? And then in my simulation, instead of using a starting velocity, I use current velocity, the velocity that I'm working with. But whenever I need to make changes to it, I make changes to current velocity so that on the next iteration, I still maintain the value of this vector that has been changed, that has the x coordinate has flipped for the next iteration. So let me run this for you. So I'm going to reset my simulation and I'm going to hit execute, and you're going to see that now, boom, it just went ahead and it bounced it off from the x coordinate. And now it goes infinitely to let me move this a little bit this way. So I'm going to reset this again, and it's going that way, and it bounces off, and then it goes that, but it doesn't bounce off this from this other boundary. Why doesn't it? Well, because I need to add a little bit of more of code. So right now, it's only going out of bounds if the x location is greater than the width. But we can add here another, or if location x is smaller than 0, so that would be this boundary here, then also flip the direction of the velocity. So for example, I'm going to reset, I'm going to kickstart this, it's going that way, it's going to go that way, and then it's going to keep bouncing between x width and x0. All right. Beautiful. That's great. But now, of course, we need to make it bounce also from the y equals 0 and y equals the height. So that just only takes a little bit of extra code to say here if location dot y is greater than boundary dot height, or location dot y is smaller than 0, then flip the y coordinate of current velocity. All right, current velocity dot y equals minus current velocity dot y. Beautiful. Shall we try this? Let's try it. I reset and then we go ahead, bounce, we bounce, we bounce. Can we make this a little faster? Let's do it a little faster. Ooh. All right. Okay, this looks like fun. All right. Now, maybe something that I may want to do is I may want to turn this into some kind of visualization. So I may want to be able to see the footprint of this point moving and bouncing across the boundaries, right? So maybe what I can do is like every time I move, what I can have is some kind of permanent polyline so that every time I move the point, I add another step to that polyline, and then I can see the progress of the point over time. Okay, let's do that. So I'm going to add another output here that I'm going to call T. That's going to be the trace. I'm going to call this the trace. And I'm going to add here a permanent polyline. So I'm going to add here a polyline that I'm going to call the trace, and I'm going to just initialize a new polyline. It's going to be an empty one, all right? And I'm also going to do this whenever we reset. We want to make sure that the polyline is blank. It has nothing on it. So I'm going to say here trace. I could do trace clear to just like empty it from, or I can just say, well, let's just make this a new polyline, all right? Before I forget, I'm also going to output it here. So that's going to be the trace, okay? And then the only thing that I need to do is I'm going to add here bounds of boundaries. And here add current location to the footprint polyline, if you will. So what I can do here is to the trace, which is a polyline that I started empty, I can every frame, I can add a new point. So that's, I can add XYZ, or I can add a new point that I need, and I know that this is going to be location. All right. And I'm going to output this here. All right. You excited? Let's try this out. So I'm going to reset and then poo, poo, poo. All right, that's kind of cool. I'm going to, all right. That is actually kind of cool. I like it. Now, just for the sake of visual output as well, I'm going to output the vector, the velocity, so that we can see how the velocity is changing over time. So I'm going to add here another output that is going to be V, and I'm going to output here over V, I'm going to output the current velocity, all right? And I'm going to use a vector visualization to anchor on the point to visualize that vector. To visualize this vector here, okay? So I'm going to run this, and then you can see I have this, and I have the point that is moving, and I'm going to move this perhaps here. I'm going to reset it again. I have the point that is moving, and I have the vector that is showing the changing velocity over time, etc., etc. So, hooray! This looks cool to me. No? Isn't this cool? You like it? All right. As you may have noticed, because I'm taking a few shortcuts, something that is happening is that the point is actually not The point is actually not stopping exactly at the boundary. And when it bounces off from farther down. That is because if I have a boundary here and my point at any iteration is like this, is right here, but the vector is longer, then on the next, like this, the velocity vector, then on the next iteration, that point is going to be somewhere here. And then at that point is when we flip the vector, and then in the next iteration, it's going to end up somewhere here. So there are ways we could do more calculations to say, well, when the point went off from the boundary, let's calculate how far off it went, and then let's subtract that from the location of the point so that at that instance, so if we were here, let's just calculate how much this was and how much this was, and then let's roll the point back here, and then let's flip the velocity now, okay? But that I am going to leave up to you, the viewer, to do as an exercise to improve this. And if you actually make it happen, I will be more than welcome to invite you to put a link on the comments of this video to your exercise and to share with the community, etc., etc. All right. Okay, I think this was cool. So what we're going to try next is do a bit more of a dynamic simulation where we're going to try and have a pendulum bouncing over gravity. Let's see how that looks like. All right, was this cool? Did you like this? Okay, so I'm going to take a 1 minute break and I'll be right back. Okay, give me a second. Right, I'm back. Forgot to say that something that is cool. I can say that. I can say that. Oh, and I forgot to say something that is pretty cool about this is that because we created a polyline that is a trace, we have that polyline as geometry that we can actually bake, for example. And now I can just take this polyline and use it as a pattern and like explode it or like, I don't know, use it as some kind of design element, which is also pretty cool. So, oh, I don't know. What did I do? I just deleted some control points. Okay, so let's go to the pendulum example. Save this as well. This is going to be E6. That okay. We got this here, so this is working great. How's everyone doing? Andres, coffee? I know, I know. Perhaps should have done more coffee myself too, but it's fine. Um, So what is next? I have an example of what I wanted to do. Okay, so that is going to be something like this. I'm just going to keep it here on the side so that I can look at it as an example. I'm going to turn everything off here. I'm going to start with something like, I'm just going to start with reset and anchor point. I'm going to start point. Mm, and I'm going to say radius, for example. Yum. And this is going to be a button here. And then this is going to be the 2 points that I already used. Can you hear the construction? Daniel, you've had too much coffee? I have not had enough coffee today. Clearly. Anchor point, starting point. So those, I see them here. Okay. And then the radius is going to be like some value, whatever. I don't know. Okay. Then we start with a line. S is going to be a sphere. To dock all of these here to one side. And then there is a point 3D. It's a starting point 3D. And this is a double. And should I already put gravity here? Fine. Let's put gravity. And so that's going to be a C vector that is multiplied by -1. Okay. For example, and this is going to be a vector 3D. All right. I'm going to plug here a panel, geometries, and more geometry. Testing, testing, sound. Yes, it's still good. So I have gone ahead and created like a C# script component that has a Boolean input that I've already typed, which is going to be the reset. Then I am going to do here an anchor point, that is where the pendulum is going to be swinging around. Then I have created here a starting point, which is where the pendulum is going to be. And then we're going to imagine that this is some kind of heavy ball that is like swinging around the pendulum, right? So that's why I've created this radius, and I have defined also a vector called gravity that is pointing down. All right. So I can now go into my code and say, well, let me write the algorithms, but then let's also output some stuff. And for starters, just for visualization, what I'm going to do is over L, I'm going to output a line that is going to represent like a spring between the anchor point and where the ball is. I'm going to say this is a new line between the anchor point and the start point, just for visualization right now. And S is going to be a sphere that is going to have the radius that we have defined and the input. So that's going to be a new sphere, which is going to be centered at the start point, and it's going to have a radius, whatever the value we're bringing in here. Okay, so we do this, and now we have this visualization. We have the ball with the radius 1, and we have this line that represents a spring between the both of two, right? Okay, so let me draw. Let's go to the whiteboard before we move on. System here. Have another point. Another point here. And then uh, on top of that, we have, we have the line between them, and we have the, oh, but that's just for visualization. We don't care here. What we care is that every iteration, we're going to have to calculate a couple things. First, we're going to have to move this point based on gravity. All right, so that's one thing. The other thing that we will need to do is, because we have a spring, that spring will tend to make the point go in the spring direction. Therefore, if we add them together, the result is that we get a vector. Oh no, what happened? Oh no, did I lose it again? Oh no, I lost it again? Why does this keep happening? Oh no. I need to find a more reliable method to do this. Okay. I'm not closing. Yes. All right. Okay. And then, okay, let me connect. Sorry, let me connect to the wireless display again. Okay, so here and okay, I should be connected again, and I should be able to now draw. Okay. Which will make my, well, that's a very fat. Okay, so the resultant should be it's going to be this vector, and it's going to give me a new location right here, and then the new location will be here. Why did it fail again? This thing is lame. Okay, you can see it here, and then I would have another thing right here, another ball right here. I think I'm just gonna tell the story here because I don't really need to. Okay. Okay. So let me start. So if we imagine we have the simulation, in the simulation, what we really care about is two main things. What we really care about is first, the anchor point, which is going to be a point that is never going to move from its location. And we care about this other secondary point, which is the point that defines the center of the ball and which we need to constantly update its location because that's what we're doing with this dynamic simulation. Everything else, the line, the sphere, whatever, is just for visual flavor, but we don't really need it or use it for any kind of simulation. So, in order to perform this simulation, the ball or the center of that ball is going to always be subject to two main forces. In the first one is going to be gravity. So, if nothing else was around, the point will tend to just go down negative c or whatever the direction. I mean, we can make gravity go in the positive x direction, it doesn't really matter, but the ball will tend to move down in the negative x direction. So that's going to be the force of gravity. But at the same time, there is this other force. We assume that the point is connected to the anchor by a line that has a certain degree of elasticity. Okay, we're going to call this a spring. And what that means is that the farther the ball goes away from the anchor point, the more the spring is pulling back and trying to bring the ball back closer to the anchor. So there is another force that is going to be the spring force that is pulling back, and it's always going to be pulling in the direction of the center to the anchor point. So we're always going to have a pair of forces, gravity pointing down and the spring force pointing in the direction of the anchor point. If we add those two together, then that is going to be the main force that is going to be affecting the motion of the center of the ball at any given iteration of our simulation. And you can see how in this case it kind of makes sense that the ball is going to swing like a little bit to the left, and then but this, as soon as it goes too much to the left, it will start swinging to the right, etc., etc. What that means is that in the next iteration, the location of the center of the ball will be somewhere here, and then everything else now. So this is going to be the situation of where the ball and the spring are on the next iteration of the simulation. Does that make sense? So at the end of the day, it boils down to figuring out what are all the forces that are affecting the particle that we are interested in, that is the center of the ball, adding them, calculating each one of them based on whatever rules. So gravity is just vertical, the spring will have its own rules, etc. Calculating the resultant of all of them and applying it to the pendulum. All right. Now, code-wise, let's see how that looks. Let's go back to Grasshopper. All right, and my computer is still frozen. That sucks. I'm going to move this here. That kind of sucks. All right, so we switch here. Okay, we minimize this. And so we need to start coding. Hey, Arasto, good morning. So we need to start coding. I think my other computer needs an update. That's why it's complaining. That. So I'm just going to update the other computer and hopefully that will make things better. All right. Okay. So we were going to write code for this. Beautiful. Let's get hands on. So I'm going to open this and then You saw how I was using here just visualization. All right. So what are the things that are going to be changing over the course of our simulation? So we said that we're going to have something called current location that needs to be a point, and we're going to initialize it to something like unset, which is a very Rhino thing. And we're also going to we're going to create a current velocity, which is going to be equal. That's going to be the current velocity is going to be the vector that is going to be defining the tendency of where the circle, the ball, wants to go to. That's going to be vector 3D dot unset. And as we did before, if reset is true, then if reset is true, what I'm going to do is that I'm going to initialize these two values to some initial values so that I can kickstart the simulation. So how am I going to do that? Well, current location is going to initialize always to the starting point. So that's going to be this point here will be the starting location. And then current velocity, in this case, as opposed to the previous example, I didn't really input an initial velocity. We have gravity, but if we start a simulation, we can imagine how if I were to grab this with my fingers, the ball, and then release it, it will kind of start with zero velocity. And then gravity will start accelerating this velocity in the negative direction, right? So I think in this case, we can probably initialize the vector to just be nothing. So we can be a new vector 3D 0, 0, 0, or even we can do it even simpler. We can just say this is going to be a zero vector, which is the exact same thing that I just typed before. Okay, beautiful. So I'm going to test this. I'm going to put a trigger. What is the trigger? I'm going to put a trigger here. I'm going to set the interval to 200. I'm going to start it. And then, okay, so I'm resetting it and nothing is happening. So that's fine. I'm going to add here an output called P. That's going to be the point that we want. And I'm also going to output another output called V, which is going to be the velocity vector. And I am going to now plug here a geometry and then display vector. I'm also going to display this vector based on this anchor point. All right, like I did before. This is going to be for me to see the velocity of this particle. Now, we haven't done anything yet here, so we are not simulating anything. So let's start. So what I'm going to do is I'm going to first calculate all forces acting on the particle. And remember, the particle that I care about is the center of the ball. So the first one is going to be gravity. All right. Vector 3D gravity is going to be gravity, which it's always going to be taken from the output. All right. Let's put a pin. Let's put a pin on. Let's not care too much about the spring right now. Let's imagine that I've calculated all the forces. All right, and then I'm going to calculate the total. Total forces is going to be equal to just gravity. I will add more forces later on. All right. What this means is that now what I want to do is I want to update the current velocity with all the acting forces. The idea here is that the ball is moving, and as it's moving, it has some kind of inertia. It's like moving in a particular direction. The forces, what they do is they change the tendency of the motion of that direction. So think of them as accelerations, for example. So because they're accelerations, they change the rate at which the speed is moving in one direction or the other. So the way we do that here is we calculate all the forces, and then once we have calculated them, we take whatever the current velocity is, so the ball is tending to go in one direction, and we modify that by the total forces that we have calculated already. Okay, so that's going to make it the vector was moving very large in this direction. Maybe now it moves a little down because gravity is pushing in, or maybe it goes back up because the spring is pulling back, etc., etc. Right? And now update the location based on the velocity. So we say whatever current location is, make sure that you update its position based on the current velocity. All right. And let's output stuff. So P is going to be current location, and then V is going to be current velocity. And I think we are ready to see if things work out. So this is running. I'm going to reset this, and you can see how the point is moving. And you can see how, I don't know if you can notice, the point starts very slow, but it's going faster and faster and faster down with gravity. And you can see how the arrow is also getting longer, correct? That's actually how things work in the real world. In the real world, if you're free falling, because gravity is an acceleration, what it makes is the velocity at which you're going down rises or increases the longer you're free falling, correct? So that's what we're seeing here. You can see how it moves faster and it accelerates, the vector becomes larger. Beautiful. So it looks like things are working so far. So, but the point went in somewhere to the infinitum, and also the line and the sphere are not updating. That is because when I did it initially, I used starting point as the location, but now that I have a point that is moving, then I should replace that. All right. And now you can see how now the pendulum is just moving like infinitely in the negative z direction, correct? So this line, which we're using to represent the spring, is really not pulling back at all, back into closer to the anchor. Okay, so let's see how would we do to now add the spring force that is acting on the pendulum into the simulation. Hey, no, no, no. How are you doing? How is the sound sounding? I'm using the new microphone. Is it good? Do I have echo? Do I have background noise? Let me know in the chat. Right. In order to model the spring, the force of the spring, we're going to use Hooke's law. And Hooke's law is a very simple physics law that says that the force that a spring brings into a system is linearly proportional of how stretched or how compressed that spring is. So the more stretched it is, the more force it's trying to applying to counteract that stretching. And if you compress the hook, the more you compress it, the more the spring is trying to like spring back out of itself, right? And that proportion is linear and is defined by a very simple rule, which is that the force that the spring the force that the spring applies to the system is proportional to x, which is how far it is from its rest length, so its original length, times k, which is a factor that is called the stiffness factor. And it's just a number that depends on the physical configuration of the spring, etc., etc. But it's just simply one number. And the whole system is negative, because if you're pulling a string, the string is has a force that is in the negative direction, in the opposite direction. And if you're compressing a string, the spring is pushing back in the opposite direction. So that's why this force is negative to where you're actually moving, how far away you are from your rest length. Okay, beautiful. So if that's the case, then how do we model that numerically? Well, first of all, we're going to introduce a new parameter that is going to be the stiffness. All right. And that's going to be some kind of value. I don't know. So I'm going to model this as, I don't know. I think we could probably do like a small value, maybe. So let's try it with 0.1. I'm not even sure. We will calibrate this when we perform the simulation. And stiffness is going to be a Boolean, sorry, a double. It's going to be a number. Once we have this, then what we need to do is we will also need to calculate the other force that is acting on the system, which is the spring. The spring is going to be a vector. Okay, so it's going to be a spring force, and I'm going to remove gravity force. I'm going to froze gravity force, and I'm going to rename this here. And then spring force is going to be equal to, as we said, it's going to be equal to negative the stiffness, so minus whatever stiffness value is coming in as an input, times x, which is the direct, which is how far off we are from the rest length. Okay. In this case, we're going to assume that the rest length is 0. So we're going to assume that we're just going to use that literally the distance between where we are and where we should be. So this is going to be the distance between the current location and the anchor point. So that's going to be current location minus anchor point, which is because both of them, because one is a point and another one is a point, when we add them together, when we subtract them, they give me a vector, and so that we have a direction that we amplify by the stiffness. Okay, so that's going to be the spring force. Then, when I calculate all the forces, I'm going to add here also the spring force. And then the rest is going to be the same because velocity is incremented by all the forces together and location is changed by the velocity. So let's see if this works. I'm going to run this and I'm going to, whoa, can you see this? All right. I can see that this vector is the vector for the pendulum, all right? And you can see it's not exactly a pendulum like hanging from a chain because I have given this line some elasticity so I can stretch it out. But we can see that it's bouncing back and forth between the origin point, the starting point, and this other point that is the result of. And you see how the farther we get, the more this spring pulls back, and that's why it's going back. All right. One last thing that I would like to add. Well, we can also see that because this simulation is always based on, the spring force is always based on the anchor point. If I actually move the anchor point around, this is actually going to change, which is kind of cool. You can see how if I move it, then the simulation, what? You can see how the pendulum is kind of like circling infinitely around this new anchor point. You see, and it's going down, but it's going also back up, which is kind of cool. All right. But this is not very real, if you will, because as you can see, this is going to be bouncing around infinitely. Okay. And in the real world, this would not happen because we have air, and the ball, when it moves through air, the air is reducing the velocity of the object in motion, and that is because the air has some friction with the ball. All right. So friction is typically a component that we often use to bring dynamic simulations to an equilibrium. Okay, to an end, if you will. Friction is typically, I'm going to stop this. Friction is typically modeled when we do physics simulation. It's typically modeled as a number. So I'm going to here write a double, and I'm going to put a value from 0 to 1. Friction is typically a value from 0 to 1. I'm going to type here 0.98, which we basically use to damp down a little, to reduce just a tiny bit the overall results of all the forces in the system. So the idea is that if we have here all the forces, we calculate them, we change the velocity based on that system, based on those forces, and then after that, what we do is we change. We're going to damp down velocity a little, assuming friction on the system. So what we do is we say, whatever the velocity was, the calculated one, let's just reduce it a tiny bit. So whatever current velocity is, let's just multiply it by a tiny factor like 0.99%, 0.98%. In this case, the value that we're getting from friction at the input, so that the velocity gets reduced a tiny bit, and the aggregation of reducing this velocity over and over every iteration will eventually bring the system to an equilibrium. So I'm going to simulate this, and you can see, do positive, and you can see how the ball is not reaching this point anymore. It stopped here, and now it's going to stop before, and now you see how it stopped before, and now it's, let me just crank this up a little bit. All right, so you see how it eventually, over time, it ends up reaching equilibrium. Okay, and if I move this, I'm basically kicking this off again, and oh, all right. And if I move this here, this is kind of cool, right? All right. Woohoo. All right. And I can also, what is the gumball? I can also move this up a little bit and make it bounce up and down and left and right. Right? Woohoo. And again, friction will end up. So imagine if I do this, you can see how friction also feels like it's like viscosity. It's like, imagine like this thing was moving in a very dense environment, right? Like full of gooey liquid, and then it just takes like a lot of effort to actually go from one position to the next, because the motion is reduced very heavily. Whereas if friction is very little, like a value that is close to 1, then the object is much more elastic, if you will, or the simulation is loses momentum, loses velocity at a lower rate. Okay. I could also, just like I did before, I could create a polyline, and I could use a polyline to aggregate the motion of. Why not? Let's actually just do it. So let's create a P is going to be a trace. The trace is going to be a polyline called trace that I'm going to initialize here. Then trace, when I reset things, is going to, I'm just going to clear it in this case. So it's going to be an empty, I'm going to empty it out. And then every time trace.add, I'm going to add current location. And did I add my output? I did not. So I need to output T here, okay? And then I may need to recompute this, and then so that it, what is the problem here? T does not exist. It does exist. I just created it. Okay, so here, negative, etc. All right. So let's simulate this. So we have this, and then I'm going to move this here. Right. Woohoo! Nice. And I don't know. This could be some kind of I don't know, physics simulation, like the trajectory of a ship in 3D space. I have no idea. You tell me. you you tell me whatever you think this is cool for. All right. Beautiful. And I can stop this at any time. I can bake this polyline. And then this polyline becomes like this trajectory, this form that I have generated by simulating based on physics some particular effect. All right. I think this is pretty cool. Huh? Okay. All right. So with this, shall we move on to the last example in this video, which is going to be modeling a chain, an elastic chain that is going to sag between 2 points, 2 anchor points. All right. Let's give that a try. How is this sounding? Huh? Are you liking this? I think this is a lot of fun. Save this. I'm going to save this. Mm. I'm sure any of you would like be able to take this polyline and make like a nice rendering, etc. of this stuff. That would be super cool. Okay, so I'm going to close this. I'm going to reset this, and I'm going to turn everything off, I think, because we're going to move on to the next example. And in the next example, what am I going to do? In the next example, I am going to model a chain between, oh, and I had it, yes, I had an example that I had already done. Woohoo, this one is going to involve a little bit more code. Okay. And draw stuff here. Will probably, right? All right, so let me reset this thing. What are we going to do? Oh yes. First I need to project to my wireless display, which is not showing up here, which is not good. Okay. Come on. There you go. Boop. Right. And then I'm going to, oh no, I have the sketchbook here, loading window. So we had this. So that's fine. I need to do a new one. And what are we going to do? We're going to model. We have 2 points. One. I need to learn how to draw better. 1 and 2. And what we want to do is we want to model some kind of relaxation that it looks like this. Okay. In order to do that, what we will need to do is we will need to start from some kind, we can model lines. So we need to talk about how basically it's all about creating a system that we subdivide into points. And then at any given moment, what we do is we calculate this. And then for each particle, we're going to have several forces. So one is going to be the gravity. One will be gravity. The other one will be the force of this spring here, and the other one will be the force. The other one will be the force of this other spring here. And because I have them all, then maybe, so that will result in some kind of vector, something like this. That was a terrible vector. That will move the point. And then we will have vectors for each one of them based on this, except for the anchors. All right, I think that is a good story to tell. All right. Okay, so the way we're going to do this is going to be very simple. What we want to model is the elastic deformation that a chain made out of springs, for example, would suffer under gravity. And the way we're going to do that is that we have, for example, 2 points, and what we want to model is the curvature that it will get over time as it bounces off and it ends up relaxing and reaching equilibrium. When it comes to physics simulations, because we're using computers to do these simulations, we can't really model the perfect continuity that a rope or like a continuous element would have sagging under its own weight. That is not really a possibility. So what we do actually in the real world is that what we model is the initial system. We assimilate that the system is made out of a discrete amount of particles. So if we start with a straight line between the 2 points, we basically subdivide this in however many points we want to use to simulate this element. And the more points, the more perfect or the more accurate will be the curvature of the element, but it will also take more computational cycles. And then what we do is once we have those, we calculate at every iteration of the simulation how these nodes are moving in three-dimensional space, so that we make this simulation evolve. Now, when it comes to designing the simulation of each one of those nodes, we actually use very similar techniques to what we have done in the previous examples. So for every node, what I do is basically think, well, which are the forces that are acting on any of the nodes of my rope, for example, or my chain. And that is going to be, for example, one of them will be gravity. So all the nodes will be affected by some kind of gravity. And then the other one will be that because each node is connected to the nearby nodes or the neighboring nodes, we will have, if we model this with in an elastic way with springs, we will have some kind of spring elasticity from the node that is on the left, pulling back to that side. And we will also have some kind of elasticity from the spring that is on the other side, and it's pulling, and basically the node is being pulled between the two springs, correct? If we add them all together, we will have some kind of resultant force, which is the one that is actually acting on the system. And if we just do this every iteration for all the nodes, then we will basically be able to move them around and design what is the final location that they will achieve after they've been bouncing and moving around for a certain amount of time. Okay, we will also introduce friction to make sure that the system reaches equilibrium. We will do this for all the nodes except for the ones that are considered anchors and that are considered immutable, that don't move in three-dimensional space. Okay. All right, so it's going to take a little bit more of code than in the previous examples, but conceptually, it's actually pretty much the same. All right, so let's take a look at how to actually do that. Thinking right now that because I'm actually thinking right now that because this video is getting too long, what I may do is I may just subdivide it in three. I may actually just edit and make three videos out of this. So I may want to record three introductions. I need to remember that. Okay. Mm-hmm. Okay, I may just say that during the introduction. All right, so I'm going to move this here, and then I'm going to just uh, I did not end up using the mass before. That was unfortunate. Well, I can probably just copy the whole thing. No? Yeah, I'm just gonna copy the whole thing and clean up the code. Um, Clean up the code here, and then this is going to be anchor 0. This is going to be anchor 1. What else do we have? We have um, how many nodes I'm going to subdivide this into. That's going to be node count, and that's going to be an integer, which I'm going to, for example, let's say 10. 10 is going to be fine. Right, and then we're going to have this, I'm going to call it mass, gravity, stiffness, and friction. Okay. And then I'm going to say that these are the points, these are the velocities, and this is the curve, for example, which is going to be a polyline, for example. The inputs correctly. Okay, let's start. So as I have done before, I have gone ahead and dropped here a C# component that has a bunch of inputs. So I'm going to have a Boolean that is going to be resetting the simulation. I have the 2 points that I'm bringing in from Rhino, which are going to be the anchors that I'm going to be using in my system, anchor 0 and anchor 1. And then what I'm going to do as well is that I have added a new input, which is the amount of nodes that my system is going to have. So that is going to be, as I showed in the example before, how many particles am I going to be modeling? All right. And this will make the simulation faster or slower, but also more refined or less refined. Something that we have been doing before, we have added the radius of the ball in the previous simulations, but we haven't actually used that radius as a way of saying that if I have more mass, then gravity is going to pull this object more to the ground. Okay, so I need to remember to do this in this example. So I have added mass, the mass of the particles, as an input to the system as well. We have gravity, which is a vector, and we also have stiffness and frictions, which are just two numbers that are going to affect the elasticity of the rope, but also friction is going to affect how much the system is going to damp down over time. Okay? And that's about it. So we're going to go ahead. I have created outputs for the points of the simulation, so the nodes. V is going to be the velocities that I'm also going to be plotting in real time. And C is going to be like a shape that I'm going to create through the inputs. All right. I'm going to drop geometry components so that we can see all of these. And I'm also going to drop here a vector display so that we can see whenever we get these, we can see the vectors displayed here on the screen. All right. Beautiful. So what are we going to do then? Well, first of all, what I would like to do is I would like to go ahead and define what is going to be part of my algorithm and what is going to be what are going to be my outputs. Okay. I am just like very OCD about that, as you probably already know. And then the next thing I'm going to do is I would like to make sure that I have here in my custom additional code, I have variables that define what is persistent, what I need to keep between iterations of my simulation so that I can have those values available across simulations and change them over time. In the previous examples, I have done one point, like location, and I have done one velocity, the current velocity. But because now I'm modeling a multi-particle system, it's not just one. In this case, I cannot use just one element. So what I will need to do is I will need to create lists of particles and lists of velocities, each one corresponding each one of those particles. I could do this with classes, so I could create a node class, I could create a force class, and blah, blah, blah. And that would actually be an amazing exercise, which maybe we will do in the future, because I've gotten a lot of requests to do a dedicated playlist on physics simulation. So that may happen at some point, but it's not going to happen anytime soon, right? Okay. But if it will, maybe it will pop up as a card somewhere here, etc., etc. But I'm going to do it like a little bit raw. So I'm going to just handle all of these elements manually independently as opposed to creating classes for it. Okay. So what I'm going to do is I'm going to create a list of point 3D objects, which is going to be the nodes. And I'm going to not initialize it, or I could initialize it to empty. That would also work. All right. And then I'm going to create also a list of vector 3D objects, which are going to be the velocities. And I'm also going to initialize this to empty. Why not? Okay, cool. So I'm going to maintain always two lists, one of nodes and one of corresponding velocities for each one of those nodes. Then when we reset the simulation, as we have seen in previous examples, what I would like to do is I would like to make sure that I don't have anything on this list. So I'm going to say nodes clear, okay, and velocities clear. So I'm going to start from scratch. All right, beautiful. But because I start from scratch, something that I would need to do as well is I would need to say, well, given how many nodes I have on my system, what I would like to do is I would like to create an initial set of particles that corresponds to this amount of nodes, and then use those as the starting points of my simulation. So here, when I reset the algorithm, what I will need to do is I will need to figure out how to create a set of points that are equally distributed between the anchor 0 and anchor 1. All right. There are multiple ways to do that. So we could just do it manually. We could calculate the coordinates and do a for loop, etc., etc. I'm just perhaps going to use a more convoluted way, which is I'm going to be using Rhino Common, and I'm going to be dividing that line, and I'm going to be dividing into a set amount of segments. Okay, but we could do this manually in a very easy way. We could just calculate the difference of, maybe that's actually a good exercise to do. So maybe I could do that, but I'm going to stick to random. So what I'm going to do is, first of all, I'm going to create a line that which is going to be a new line from anchor 0 to anchor 1. All right? Then I would like to subdivide that line into an amount of points. The problem is that lines in Rhino don't have a subdivision method. So what I need to do first is I need to convert it. This is the convoluted way. Line curve, I need to convert it to a nerves curve. So I need to say line dot and then to nerves curve. Basically, it's the same object, but internally, instead of being represented as a line, which is just the two ends, it's a nerves curve. And because it's a nerves curve now, I can take that curve and divide it by an amount of points. So you know that line curve, because it's a curve, now I can say divide by count. And I can design how many elements, how many segments I want to divide this by. So divide by count is going to say how many segments do you want to divide. Remember that my input says how many nodes. And here I've been asked how many segments. So if I divide a curve into 2 segments, I will get 3 nodes. If I divide a curve into 3 segments, I get 4 nodes. So here what I need to do is I need to divide by the amount of nodes minus 1. All right. And I do want to include my endpoints. All right. And if I do this, be able to see that what this function is giving me in return is actually not the points, but is an array of doubles. So let me show that again. It's an array of doubles. This is because the function is designed to give you the parameters as values at which those divisions will happen. However, thankfully there's an overload that already gives me, as well as part of an out parameter, it gives me the actual points on those parameters so that I don't have to now go with a for loop and each one of the parameters and like extract that point from the curve. So what I can say is, oh, I want this to go into a variable which is going to be an array of 3D points called PTS, and before I run this code, I need to create that variable, an array of 3D points called PTS. Okay? Beautiful. And since I'm not going to be using the parameters that this function returns, then I don't need to actually store that in any variable. This is what I'm interested in, these points. Then, okay, so now I have all those points. So now I can say nodes, can you add a range? And that's going to be all these points that I just generated. To make sure that this is working, what I'm going to do is I'm going to now go to the outputs and say the outputs has to be all those nodes. And if I press reset, you can see that I got all the nodes 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, so this is correct. I got all my points here, all my nodes, and I can start simulating those nodes. I can start simulating those nodes now. All right. Similarly, for the velocities, remember we need to initialize those velocities. So if I have 10 nodes, what I will need to do is I will need to create 10 velocities which start at 0. So what I'm going to do is I'm going to say for int I equals 0, I is less than node count and I plus plus. What I'm going to do is I'm going to say to the velocities list, I'm going to add a new vector that is going to be a 0 vector. So I could do this, or I could just say a new vector 3D, which is 0, 0, and 0. Both work the exact same thing. Okay? And then also for the sake of visualization, I'm going to output that through the output. So now I have velocities. I'm going to reset this. And you can see that I have all these zero vectors, and that's why they're not showing here because there's zero vectors, but they are. Okay, beautiful. So this is great. And I think at this point, we are ready to start the simulation. What are we going to do? Well, just like we did in the previous examples, the only thing that we need to do is we need to go through each one of these nodes, each one of the points. And for each point, what I need to do is I need to calculate what is the gravity for that point, what is the spring for with the node on the left, what is the spring with the node on the right, and then add them together and add them to the current velocity, apply some friction, etc., etc. All right. Before I do that, I'm going to turn on my light, which just went off. Great. My face is all shiny and bright again now. Okay. Also, before we forget, I'm going to here on the outputs, I'm going to create a polyline, which is going to be, I'm going to call it I don't know, the chain, which is going to be a new polyline with all the nodes as inputs. And actually, I can just output that directly over C. All right. And then, oh, this is not working. C is a new polyline. Okay, so I'll take a look at why this is not working at some point soon. Okay. All right, beautiful. So now inside of the actual simulation, so we need to start simulating. All right, simulate forces for each node. So what I'm going to do is I'm going to go with a for loop and I'm going to say int I equals 0, I is less than nodes dot count, and I plus plus. All right. And this is great, but this is not going to work, okay? Because think about this. In this case, due to how I have arranged my simulation, it turns out that the points at the ends, the first point and the last point of my list of nodes are anchors, and those points should not go anywhere or should not move. Therefore, I should probably not run a simulation that is going to look at all the nodes from 0 to node count -1 or whatever this one is. Okay? So what I will need to do is I will need to start with node in position number 1 and end with node in position count -1, which will be this one. So if that's true, then I need to modify my for loop and say, instead of starting at 0, I'm going to start at 1. And instead of ending at count, I'm going to end at count -1. And just because I want to be very verbose, I'm going to say point 3D P or N is going to be equal to, from the list of nodes, element in position number I. And vector 3D V is going to be nodes, velocities in position number I. Okay, beautiful. So now that we have this, I can use this to read information and to start calculating. Let's start calculating all the forces. So for example, vector 3D gravity force is going to be equal to gravity. Okay. However, this is what they didn't do before. Gravity is typically multiplied by the mass, because objects that are heavier have more gravity than objects that are not. Okay. So this is something that we didn't do in the previous exercises. And that's why we calculate it independently. All right. Now let's calculate the spring force with the previous node. Okay, so for example, let's say vector previous spring, the spring with the previous node. So that's going to be equal to minus the stiffness, as we saw in the previous example, and then the distance between this node and the previous node. So this node is n, so this point, and then the previous, the one on the left is going to be, from the list of nodes, is going to be the one that is in position I minus 1. All right? This is a point, this is another point. When I subtract them, I get a vector, so that the whole thing is a vector that is scaled by the stiffness. Now, vector 3D next spring, same thing, is going to be equal to minus stiffness times the distance between the node that we're looking at right now and the one that is next on the list. So the one to the right, if you will. So that's going to be n minus nodes I plus 1. So the one that is right next. And this is also the reason, because we're looking at the previous one and we're looking at the last one, this is also the reason why we need to start with 1 and we need to end 1 unit before, because then if we don't do this, we will not have nodes on the sides to compare with. All right? Beautiful. So let's aggregate all the forces. All right, so let's say vector 3D total force is going to be equal to gravity force plus previous spring plus next spring. So now we have the total. All right, now let's update velocity with this value. So we're going to say V is going to be increased by the total force. Now, let's add some friction. We saw this before in the previous example. V is going to be multiplied by some friction. All right? And then let's update the location of the node. So N is going to be increased by the value of V, this velocity that we just modified. All right? And now what we're going to do is that this would not be enough, because it just so happens that this is a very technical thing. Point 3Ds and vector 3Ds are structs, and when we read them from a list, we read them by value, not by reference. So all the changes that we have done to N and V are only going to be from this are going to be only affecting these two local variables, N and V, but are not going to be affecting the actual node on the list and the actual velocity on the list. So what I need to do now is I need to update values on the original lists. So what I need to remember is I need to say nodes in position I is going to be equal to this new modified value that I have now, which is n. And for velocities in position y, I also need to overwrite that and say that I have updated this value with this variable that I've computed that is called v. All right? And I think with that, we should be ready to go. Let's actually see how this would work if I only had stiffness, if I only have had the gravity. So right now this is not working. Previous spring that all right. Okay, so let's just see the whole thing working, and that's it. So oops. Okay, so this is going to work, and then I'm going to reset this, and then I'm going to put a trigger in here, and we're going to simulate this at intervals of 200. Whoa, this is going very far. So let's reduce the mass. All right. Oops. So let's reduce the mass, and let's perhaps what? And let's reduce the stiffness. And okay, and let's create a chain between these two elements. Oh, this should be, I'm going to move this back to 0. I'm going to move, I'm going to Displace this to 0. No. Projected point. Ah, okay, and here what we're going to do is we're going to create a new polyline. C equals new polyline with all the nodes. Okay, just for visualization. And I'm going to start this, and you can see how the nodes start sagging, and at some point they reach some kind of equilibrium. I'm going to lower the mass also a little more, because perhaps it's a little too much. You see how they're dragging, and it's forming this chain, and we can see the velocity vectors dragging the chain. And let me just crank this up. All right. Ooh. Now it's bouncing back up, and I think it's uneven because this point is higher in 3D space. You can see, and if I were to make the thing more stiff, you can see it starts bouncing off. Oh, you see how it's stiffer now? Oh my God. Oh, this is something that happens very often with simulations. They become unstable because there's some kind of offset. Some of the forces are stronger than the others, and then it cannot reach equilibrium. This happens a lot, actually. The stiffness is just stronger than the weight of the elements in this case. So, all right. So this is great, except for one tiny detail that I want to improve here. What's nice about this is that we can use this for dynamic form finding. All right. So if we had a chain that we wanted to model, we could say, if we want to use this for design, I may want to say, well, this is too high here. So I wonder if I move this over here, if the chain will become more taut or like less high here. But the problem is that I just moved this, but the simulation stays as it is. It stays as it is, and it doesn't update this anchor to this new position. Why is this the case? This would only happen if I restarted the simulation again, but not if I move it while the simulation is happening. And that is because if you think of the code, the only time that we have used the anchor points, anchor 0 and anchor 1, has been when we created the new line that we then subdivided, etc., to create the nodes. But after that, every time we simulate, unless we reset, we're not taking into consideration these new anchors. So something that we can do is just to make sure that we're listening to changes in the simulation. Something that we can do is we can say here, let me just update the location of the anchors every time I simulate this system, just in case one of the inputs, just in case the user has been moving the point around. So what I can say is I can say node 0 has to be equal to anchor 0, and um, nodes dot count minus 1. So the last node has to be equal to anchor 1. So I basically override whatever values I calculated at the beginning of the simulation. I override them every time to make sure that I account for possible changes in the location of those. And if I do that, I'm going to start this. This reaches some kind of equilibrium, etc. But now I'm going to take this and I'm going to move it. And how cool is this? Huh? How cool is that the simulation is now, the springs are like moving in 3D space and like reorienting, and the chain is kind of, you see it, this side sway that it heads between, because, oh, how cool is this? Right? And I do this, and look at how all the springs are like moving around and trying to reach equilibrium, right? I mean, isn't this the coolest thing ever? Seriously. This is so cool. I love this. I just cannot express it enough. All right, beautiful. Okay, so with that, I think this is where I wanted to finish this exercise. Is this what I wanted to do? if I'm going to do three independent videos, I should record endings for each one of the three videos, and endings for the and beginnings, intros for each one of the three videos. Oh, I should have thought of that before. Yeah. And yes, so this is the end of where I wanted to get. So this is the last of the three videos in this mini series, how to create dynamic simulation in components. The first one was bouncing, making a ball bounce off some boundary. The second one was to model a pendulum. And this video has been to model an elastic chain deforming under its own weight. Okay, so I hope this was fun. I hope you learned some particle physics simulation. I also hope you learned how to use persistent data as a way to mimic uh, a continuous execution in Grasshopper components. And then maybe this is the door for you to create your own Kangaroo plugin or your own dynamic simulations and to use this for form finding, etc., etc. This is endless. It's like a really cool thing. Okay. Beautiful. So thank you very much for being here. And with this, we're going to move on to the next videos in this series. Advanced development is Grasshopper. So thank you very much. And if you liked what you saw, maybe like this video, hit the subscribe button, hit the bell button to get notifications when we go live, when we post new videos, etc., etc. See you in the next videos. Bye bye. Thank you. All right, so I'm going to record now the ending of the second video. All right, so that's going to be something like this. See where that lands. Mhm. All right, and with this, I think this is what I wanted to leave it for this second video in this mini series, Dynamic Simulation Components, where we have modeled a pendulum that is oscillated under a spring. Okay, so this is going to be awesome. That was awesome and a lot of fun. And the next video in this series is going to be a very similar idea. So also modeling particles that are affected by springs and gravity. But in this case, what we're going to do is we're going to model a chain or a rope of an elastic element, an elastic linear element that is going to deform under its own weight and under the effect of gravity. Okay? Very similar to this technique. It's going to involve like more particles and more management of the data with for loops, but like very similar in spirit. Okay, and super cool in interaction. All right. So see you on the next video. Thank you for being here. And if you liked what you saw, maybe consider hitting the like button, subscribing to the channel, etc., etc. See you. Bye bye. All right, and now I'm going to record the ending of the first example, the end video of the first example, uh, where I'm going to, yes, what's going on here? Oh, because this was super extreme. All right. Huh? What? Wait, why is this not working now? Oh, what? Oh, wait. Ah, it is working. It's just that it's because it's in 3D, it looks like it's moving. I don't want projected point. Yeah, good point. Oh, yeah, because it's moving. This is kind of cool, actually. All right. So let me stop this. So, so this point, yeah, I don't want to project. Yeah, exactly. So, so from here to 0. Stop at the boundary without relying on Rhino common is complicated. What's so complicated about it? It's actually a fairly simple vector operation, no? Just like calculating the. Uh, yeah, I guess you could argue. Hmm. All right, with this, I think we are in a good position. This is what I wanted to get with this example. So, so this was the end of the first video in this three-part series where we're going to be doing dynamic simulation components. I think what we're going to do in the next video is that I'm going to teach you how to model a system that has gravity and spring forces. Like, for example, we're going to model a pendulum that is going to be oscillating around an anchor point or something like that. Okay, so thank you very much for watching this video. You may want to show some gratitude, liking the video, subscribing to the channel, etc., etc., or not. That's perfectly fine as well. And see you on the next video. All right, let's model some pendulum. It's going to be a lot of fun. Thank you. Bye. And now I'm going to record the introduction of the three videos. Oh my god, this was complicated. Hello, this is Jose Luis here at Parametric Camp, and welcome to another video in this series, Advanced Development in Grasshopper. This video is going to be the first video in a small series of three videos where I'm going to teach you how to model dynamic simulation inside of Grasshopper mimicking continuous execution. And the first example that we're going to do in this mini series is going to be a really simple one, which is going to be taking a point in three-dimensional space, defining some kind of boundary, and then creating a simulation where for some starting velocity and some starting location, we're going to model that point moving in this boundary and bouncing off the boundaries of this region. Okay, so that's going to be a rectangle, a point, a vector, and then how this moves in three-dimensional space. You can see that this simulation is not actually perfect for the reasons that we will explain very soon, but it's going to be, the first one is going to be a warm-up to the other two videos, which will be modeling a pendulum and modeling the deformation of an elastic rope sagging under its own weight. So that's going to be the next two videos. All right. So, but this is going to be cool and fun because with this now we can model systems that dynamically change over time and that generate form. So that, for example, we can now bake this in three-dimensional space, and we can bake this and then use this as some kind of pattern or some kind of geometry that we use for a facade. Or, I mean, I don't know. It's absolutely up to you. Okay. So let's get hands-on and perhaps like go to the whiteboard first and then break down this problem, how we're going to tackle it. Okay, let's get hands-on. Right, so that was the first video. Then the second video is going to be this one. Okay, and if I press play, all right. Hello, this is Jose Luis here at Parametric Camp, and welcome to another video in our series Advanced Development in Grasshopper. So this is the second video in a three-part video where I'm teaching you how to create dynamic simulation and particle systems using Grasshopper and mimicking continuous execution. In the previous video, we saw how to take a point and make it bounce off a particular region. In this one, what I would like to model is I would like to model the effect of a pendulum that is elastically connected to an anchor point and that is affected by gravity, but it's also affected by the springiness, if you will, of that elastic connection that it has with the anchor point. So we're going to imagine we start with the pendulum here, and if I now run execute this system, you can see that the pendulum starts like swinging back and forth, and it eventually reaches some kind of equilibrium. But if I move my node, you can see that I can start affecting and reintroducing energy in the system, and then the pendulum starts like swinging crazy back and forth. And we can plot the trace of this motion in three-dimensional space. I can actually also just bake this and freeze it in time and then use this as some kind of visualization of, I don't know, the space particles of the CERN accelerator in Switzerland, etc., etc. I don't know. But I think it's actually quite cool. Okay. So with this, we're going to learn also a little bit about how to model elasticity using Hooke's law. We're going to learn about how do we overlap multiple forces in a system and how we consider them accelerations that affect velocities, that affect locations, etc., etc. All right. It's going to be a super interesting example and fun as well. So welcome and join me in writing this dynamic simulation in Grasshopper. And as usual, why don't we just start by going to the whiteboard and then drawing a sketch of what this looks like and thinking through the problem. All right, let's do that. All right. And last but not least, the intro video for this one, which is going to be this to 0, and then just all right. And is this going to Hi, this is Jose Luis here at Parametric Camp, and welcome to another video in this series, Advanced Development in Grasshopper. This is going to be the third video in this mini series, Dynamic Simulation Components, where in the previous two, we've done the point that bounces off a region, and we have modeled also a pendulum that is subject to gravity and to elastic forces. This exercise, the third one, is going to be super similar to the pendulum one. We're also going to be working with gravity, and we're also going to be working with elastic forces. But the goal of this one is to model the deformation of some kind of elastic rope or chain or linear element that is deforming under its own weight. And it's going to look something like this. So it's going to look like two anchor points with a line between them, and then some forces that are affecting the particles that we're using to model this system, you know? And we have things such as mass that we can control, the stiffness of the spring, but at the same time, we can also, as we've done in previous example, we can modify the system in real time, and then the simulation will try to adapt over time and reach some kind of equilibrium through the combination of all the forces and the friction that we have introduced in the system. All right. This is also a great example for doing form finding. If you are a fan of, like, for example, Gaudy's work and how he used chain models for form finding, this is at the core of how to simulate these processes computationally and do a similar work to what Antonio Gaudí used to do, like in the Sagrada Familia. This is going to be very similar to the second example that we did in this mini series. It's just going to involve more nodes, more velocities, and handling, just instead of one particle, managing a collection of particles that form our simulation. Okay, but it's going to be super similar in spirit and very easy and a lot of fun to implement. Okay. All right, so with this, let's get hands-on and let's go to the whiteboard and let's first think through the problem on how we're going to model this thing, okay? All right, let's get hands-on. Right. Okay, well, that took a little longer, but it's fine because I'm actually really happy with these three exercises and it's going to be cool. I think they're going to be quite useful. All right. So there's going to be no stream this afternoon because I have a lot of work to do for my real world job, you know. So I'm going to have to go back to real world issues, you know. But thank you very much for being here. And thank you, Arasto Victor Tevez. It was a pleasure. No, everyone. Thanks for being here. And I will see you back sometime, maybe next week, I guess. I don't know when we're going live again, but probably next week, Wednesday. I think Wednesdays are coming up. It's been a good day for me to do these things. All right. Thank you very much and see you in the next stream. Bye bye.